Hey, good morning, neighbors. I want to talk a little bit about a Wheatstone Bridge. What is a Wheatstone Bridge? Why would you care what a Wheatstone Bridge is as long as it doesn't fall down while you're driving over it, right? Anyway, Wheatstone Bridge is a specific configuration of resistors, basically. Now, these resistors would be tiny coils of wire, very specialized wire, engineered with specific properties, so it's a specialty metal, but that's what it is. So, that Wheatstone Bridge, on one arm of that bridge, you can tune it electronically, and by varying the size of those little coils that you made into resistors, and tune it so it can very precisely measure temperature. Isn't that odd? But that's what that little coil is doing. It's measuring as the temperature changes, the properties of that one little coil changes, and we can measure it. Gives us a number. So how useful is that? Again, we've got four arms attached in the center, and one of them has the ability to sense very precisely temperature changes. Well, if we work with that instrument and we learn its temperature characteristics, we can begin introducing specific gases to pass by it and see how they draw heat off of it. So this is the basis of many chromatographs, instruments that measure chemicals. These chemicals could be CO2, methane, they could be VOCs, types of hydrocarbons, long chain hydrocarbons, plastics. So that little Wheatstone Bridge is kept inside a cabinet that is an oven. It's very precisely temperature controlled because we need constants around that, so that all that sensor is sensing is those tiny little gas molecules flowing by and drawing heat off of that little coil, drawing energy off of that little coil. We're really talking about energies now and not temperature. But it started with temperature, so you can't lose that, right? And what we've developed is a relationship, a specific ratio between the temperature and the heat drawn off of it. Now, if we begin to sample these gases, we can find different properties. They draw heat away from that material as it flows by. It's a gas. Remember, we're flowing gas by this little coil. And the little coil is sensing these changes in the gases as it goes by. That's a chromatograph. Through a bunch of fancy numbers and computers. In the old days, you used to do this by hand. You did paper calculations. That's how it started. There weren't computers around to do this. There weren't calculators. You had slide rulers. So that Wheatstone Bridge, that little application in a gas chromatograph, what does it mean? These chromatographs looked like small pizza ovens, maybe. A small refrigerator you might have in your dorm room. That was the size of them. There was an array of them on the wall, and each one measured some specific sets of gases from specific process streams. Very precisely. That was one of my roles, was to certify and maintain the accuracy of those machines. They had to be calibrated, they had to be certified every so often. Gas bottles had to be changed. Sample systems were in trouble when I got there and redesigned those. So this was engineering. This is applied engineering, where you take things that are supposed to work in a lab and put them out into an environment that maybe has never been tested before. So one sampler's internal cabinet temperature is almost 300 degrees because it has to keep plastic as a gas. Plastic is a vapor. That was two of the instruments. Another was looking for purity of hydrogen off a process area. Process stream created high purity, 2 decimal place precision hydrogen. So it was 99.9% pure hydrogen. And that instrument had to be able to measure that level of precision. If something tuning went wrong in the process, the instruments would show it and the process would be retuned, sometimes automatically. That's artificial intelligence. So where else is that Wheatstone Bridge? When you see a chromatograph now, you can think Wheatstone. And you could go look that's electronics world, that Wheatstone Bridge. Somebody in the chemistry world got together with somebody in the electronics world and said, we can do this. Now, there's another feature to make that chromatograph work, which are fractioning columns that separate the gases, the constituents of a gas sample, into those little boluses, those little discrete packets of molecules that have been sorted and put in order. So the hydrogen comes off first because it's very light and very tiny. The methane, the CO2 would come off later. Oxygen detectors were a different type of detector. Those were in process lines looking for pollutants in feed streams. So we had analyzers looking for different gases within gases to make sure they weren't there. And they would alarm if they were. Things would shut down or things would be changed. So those chromatographs, again, this is 1980s. This is next generation systems and process controls in the chemical industry, and the applications of a Wheatstone Bridge into a gas chromatograph into a process control system to make plastic, in this case, to make 2-ethylhexanol, basically an oil used in metals manufacturing. Some of the things have to be made better. They can't be turned off. That's the challenge today. That's the challenge tomorrow. So, hope you enjoyed. Not much to look at early in the morning with coffee. Thanks for listening.